All right, so in this video, we're just going to continue with our discussion on integration by substitution. And the one we're going to look at now probably looks familiar. We actually did this one in section 5.1 where they gave you a couple formulas, a couple tables to look at. And back then, it's not a bad idea to kind of get your feet wet by using those tables. And those types of formulas that they gave you were are incredibly common moving forward. So if you do happen to memorize those, they're fine. But I do need to show you where they come from. And so for a problem like this, what we're going to do first is just go ahead and move that 1/3 out of the integral symbol. So then we would have this sine pi over 2x dx. And just like many of the other ones, we would let our substitution be the inside part. So pi over 2x, which means our du would be just the pi over 2 dx. And now when I multiply that 2 over pi on both sides, we get our substitution there. So this 2 over pi du is going to be replaced right here. So I'll come over here, I've got my 1/3 integral sine of u now times 2 over pi du. The 2 over pi can come outside of the integral symbol, so that's going to be a 2 over 3 pi integral sine u du, and the integral for sine is negative cosine, so we get our negative 2 over 3 pi cosine u plus c, and then when we make our substitution back into x's, we have our negative 2 over 3 pi cosine of pi over 2x plus c, and that's us using that formula from the beginning of chapter 5 where we had negative 1 over k cosine kx, and so our k just happened to be the pi over 2, but by a u sub, that's where those formulas come from. And if you don't want to memorize them and you want to do this every time, that's great, but for those few that you saw earlier in the course, if you happen to have them memorized, at least now you know where they come from. All right, so this one we've got some more trig, and we're going to combine what we learned in the last problem with one from the previous video here. So it doesn't look like I can manipulate this really in any other way. You've always got trig identities you can take advantage of, and I always recommend thinking through those, thinking what you can do to maybe consolidate some things using those trig identities. But unfortunately, in this case, I don't think it's going to happen. So for us, it makes most sense to let the u equal sine of 4x. Now remember guys, you're learning this for the first time, so if you're not seeing where this comes from right away, that's okay. The more you do, the more you see, the more you'll learn. But for now, we're going to let u equal this, and as it plays out, you'll see why we selected what we did. So then the du would be 4 cosine 4x dx. And if I simply multiply by 1/4, what I have left now, that cosine 4x dx, that thing right there is now going to be entirely replaced with that 1/4 du. So that's why I picked what I did. Not only did it help me come up with something easier to integrate, but it also knocked off that additional piece there that I was just kind of sitting there waiting on me. Okay, so I'll come over here now. We've got our integral u to the 5th times a 1/4 du. I'll take the 1/4 out, and then I'll add 1 and divide. So 1/4 times 1/6, u to the 6th plus c. So 1 over 24 sine to the 6th of 4x plus c. Once again, I always think it's nice, especially on these, especially early too, to take a few minutes, pause the video, take the derivative of this to confirm that it does in fact give us what it should up there. All right, so for our next example, kind of go through the same line of questioning. Can we manipulate to simply add 1 and divide, or is there something algebraically we can do to change the way this looks? Unfortunately not, so we're going to have to consider the u sub. Much like all the other ones, we try to let that u be the inside part if it works. In this case, our du would be a negative dx. Okay, so a negative du equals dx. Now, when I come over here and I write what I have, we've got a little bit of a problem, don't we? So I've got my u underneath there. My dx is being replaced with this negative du, like I have it written. I'm eventually going to take this negative 1 and pull it out, But the problem is, remember what I said earlier, if you've got a du here, you can only have u's throughout here. But we have this x squared. So what we're going to do is actually take advantage of the original substitution. When I take now this guy here and I solve it for x, I find out that x equals a 5 minus u. So now I can take this and substitute it in right there. Okay? So that negative I'm going to pull out. This is going to be a 5 minus u squared times u to the 1/2 du. Now we're in a good spot. Now we're in a spot where we have all u's and we can hopefully move forward with integration. Now before I do that though, I am going to have to, looks like, clean it up. I can't add 1 and divide like I want to term by term the way it is. So I'm going to expand this out and then I'll distribute this u to the 1/2. So we get a negative, then I'm going to have a 25 minus 10u plus u squared, all times a u to the 1/2 du. And then distributing that u to the negative 1/2, I will get 25u to the 1/2 minus 10u to the 3/2 plus u to the 5/2 du. Make sure you have that du on every single step. All right, so I think we're ready. Now we're just going to add 1 and divide all the way through. That negative I'm just going to put all the way to the outside for now. So this would be a 25 times 2/3 u to the 3/2 minus 10 times 2/5 u to the 5/2 plus 2/7 u to the 7/2 plus c. And so the last step in all of this is to plug in the 5 minus x for all the u's, as well as clean up these coefficients here. And I will also distribute the negative just to be thorough. So our final answer here looks to be a negative 50 over 3 times 5 minus x to the 3/2 plus 4 times 5 minus x to the 5/2 minus 2/7 5 minus x to the 7/2 plus c. This is one where you could still take that derivative to check. You would have a bit of work to do in simplifying to make it look like this, but it all should still work out at the end. Okay, so last problem then for the section. We've got now a definite integral, no longer indefinite. We've got a definite integral, and so we'll just ignore that for a second and proceed with our normal integration. The normal integration looks like it's going to have to be a u sub. So again, I'm thinking ahead a little bit. What can I let u equal so that when I find du, I'm going to be able to not only change my variable, but take care of all other parts of the original function. So it looks like in this case, if we let u equal sine of root x, then the du would be cosine root x back times the derivative of the inside dx. So now you're ready to make your decision on what you want to move over here and what you want to leave over here. Well, it looks to me like we've got this guy here as our entire u, therefore everything else has to be replaced. And so I like the cosine, I like the 1 over root x. It looks like the only thing I need to move would be that 2. So if I move the 2 over to the other side, then I have a cosine root x over root x dx. And so now that thing is going to be this thing right here. So a nice simple substitution, being able to think ahead a little bit, really clean this up for us a lot. Okay, so I'm going to come over here. I'm going to put my 2 right there. I've got my integral symbol. All I'm going to have is a u du. But what I want to be really careful about is that I don't put these numbers here over here. Think about why that is. What are these? Well, because of this dx right here, those are x's. That's an x equals pi over 2, or pi squared over 4, and that's an x equals pi squared. These have to be u equals because of our du. So I need to change these x's into u's. And to do that, we're just going to come right over here. If I evaluate at x equals pi squared over 4, and x equals pi squared, that should give me my top number and bottom number now in terms of u. So, for example, when I take this pi squared and I plug it in here, the square root of pi squared is pi. Sine of pi would be 0. So that would be a 0 on top. Similar on the bottom. If I take this pi squared over 4 and plug it in, that's going to give me a sine of pi over 2. And sine of pi over 2 is going to be equal to 1. So now those are the numbers we want to use, not the original, because again, we changed variables. All right, so now we're ready to integrate. I've got a 2 times 1/2 u squared. Don't worry about the constant because, again, it's going to zero out once we evaluate, since this is a definite integral from 1 to 0. So that would be a 0 squared minus a 1 squared for a final answer of -1. So these definite ones really aren't any different whatsoever until you get to the end, which is where you evaluate. But just remember, if you change the variable from the original, you also have to change the bounds from the original as well to whatever it is you change to. But that's simply done by going into the original substitution, plugging that stuff in, and you get your top and bottom numbers.